For every isotope, there is an amount of energy called the binding energy that holds the nucleus of that isotope together. This binding energy is shared between the nucleons, the protons and neutrons, which make up the nucleus. The higher the binding energy per nucleon is, the more stable the nucleus is. The binding energy per nucleon peaks at nickel-62, which makes nickel-62 the most stable nucleus. Splitting or fissioning nuclei heavier than nickel-62 results in the release of energy, and joining together or fusing nuclei lighter than nickel-62 results in the release of energy.
Nuclear fusion is the process by which two lighter nuclei are joined together to form a heavier nucleus.
Because nuclei are composed of electrically positive protons and electrically neutral neutrons, there will always be a repulsive force between nuclei as like charges repel. This means that nuclei must be pushed together by a force large enough to overcome this force of repulsion if they're to fuse. This is why fusion only occurs at very high temperatures and pressures. Particles at these temperatures and pressures are travelling very fast and will collide with enough force to overcome the repulsion between them. Fusion nuclear bombs, also known as thermonuclear bombs or H-bombs, use an initial nuclear fission stage to create the high temperatures and pressures needed to start the nuclear fusion reaction that the bomb relies on for its incredible destructive power. Some scientists have suggested that it may be possible to create fusion reactions at low temperatures, but no reliable evidence for so-called cold fusion has ever been seen.
Stars form when huge clouds of gas and dust, many billions of kilograms in mass, are compressed by the force of gravity. Eventually, the gas particles are compressed so much that the force of gravity is great enough to overcome the force of repulsion between them, and the particles begin to fuse with each other, releasing a huge amount of energy in the process. The fusion process in the Sun is a three-stage process. Two atoms first fuse to create a nucleus of deuterium. Then an atom of deuterium, also known as hydrogen-2, and another proton fuse to form a nucleus of helium-3. Finally, two helium-3 nuclei fuse to form helium-4 and 2 protons. In total, 4 protons are fused together to form one helium-4 nucleus, and in the process 26.9 mega-electron-volts of energy, or 4.3 trillionth of a joule, is released. This might not seem like a lot of energy, but it's happening on such a huge scale that the Sun produces 3.85 trillion joules of energy per second.
Trying to recreate conditions similar to those in the Sun on Earth is difficult and expensive, and is what has, as of now, prevented the creation of commercial fusion power stations. There are two major fusion energy projects. These are ITER in southern France and the National Ignition Facility in the USA that are working towards commercial nuclear fusion power. ITER plans to use magnetic confinement, compressing a high-temperature plasma with magnetic fields, to initiate nuclear fusion. The National Ignition Facility plans to use a huge array of very powerful lasers to compress fusion fuel.